Hey, welcome back everyone. Last time we covered the first 7 questions in 1D dynamic programming on the LeetCode roadmap. So today we're going to cover the remaining 5. So in the last video we covered some basic ideas of DP such as storing values, finding subproblems, and evaluating the minimum or maximum. So we're going to continue doing that today. So without further ado, let's move on to the first question, coin change. So in coin change, we're given an integer array coins representing coins in different denominations and an integer amount representing the total amount of money. So what we want to do is we want to return the fewest number of coins we need to make up that amount. Or if that amount cannot be made up by any combination, we want to return -1. So we also have an infinite number of each kind of coin. So let's look at example 1 here. In example 1, we're given coins 1 to 5, and the amount we want to make is 11. So there's a few different ways. For example, we can just make up 11 with 11 different ones, or 5 2s and a 1, or 2 5s and a 1. So which one is the fewest number of coins? Well, it's going to take the highest number. So we're going to use 5 twice and then 1 once, which is going to be 3 coins. So in example 2 here, we have a coin for $2 and we want to make $3. So obviously that's impossible because we can only make up even denominations. So this is going to net us -1, or as the question says, we cannot make up this combination. So in example 3, we have a coin of $1. The amount we want to make up is 0, and that takes 0 coins. So we don't need to use any coins. We can just output 0 because it takes 0 coins to make up $0. So to solve this question with the dynamic programming method, we're going to need to store how many coins it takes to make up a previous amount, and then use the number of coins or the different types of coins that we have here to see how many ways or how many coins it takes to make up the current amount. So in this question, we can set up our DP just like before. So DP equals to, we want to find the minimum amount of coins to make up each denomination. So DP is going to be initially set to the highest number. That way we can compare with what we have now in DP to find the minimum number. So to find the highest number, we can just use 1E9. This is 1 billion. So this is probably going to be higher than any amount of coins, since coin's length is pretty small and the amount is pretty small compared to 1 billion. So we're going to set this to 1 billion times the amount plus 1 because we want an array starting from index 0 all the way to index amount. So we're going to have amount plus 1 elements in there. So after that, we're going to set DP at 0 equals to 0. This is because of this example here, which is saying that if we want to make up an amount of 0, all that takes is 0 coins. So it doesn't matter what we have in coins, DP0 is always going to be 0. So now we're looking at amounts that are greater than 0. So for I in range, starting from the amount 1 all the way to amount plus 1. So this is non-inclusive, so we're going to end up with I equaling amount. So now at this amount, we want to try every coin we have. So for C in coins, C is the value of the coin. So we have an amount I, and then we want to see if we can use the current amount C to add up to a previous amount to I. So it's essentially the previous amount is going to be equal to I minus C. So in example 1 here, for example, we're looking at coin 1 and I is at 1. So I minus C is going to equal to 0. We set DP at 0 equals to 0. So previous is going to be 0. So first we need to make sure previous is actually in the array. So previous has to be greater than or equal to 0. So if previous is greater than or equal to 0, we can set DP at I. This could equal to how many coins it takes to make up the previous amount. So DP at prev. However, it's going to take 1 more, so it's going to be plus 1. But at the same time, could be multiple ways to make up DPI, so we want to find the minimum of those. That's why we set DPI to be really high before, so we can use minimum to compare and find the minimum. So it's going to be min DP at I compared with DP prev plus 1, which is how many coins it takes to make up the previous amount plus this 1 coin that we're using right now. So after that, we can just return DP amount. However, there's another catch to this question. It's because sometimes we can't actually make up that amount. For example, if coins is 2, amount is 3, we want to return -1. So we want to return dp amount if and only if dp amount is not equal to 1 billion or 1E9. Because if it is equal to 1 billion, that means this min was never run, since it's impossible that dpprev plus 1 is going to be 1 billion in our question's case. So if it's equal to 1 billion, that means we never found a way to make up dpi, in which case we want to return -1. So else -1. Let's try running this. Cool, it's accepted. Nice. So this question is pretty much breaking the amount challenge into different smaller subproblems where we make up smaller amounts from 0 all the way until the actual amount that we want. So because we can see how many coins it takes to make previous amounts, we can try adding the coin's value plus 1 onto the number of coins it takes to make up the previous amount to see how many coins it takes to make up the current amount. And then out of those options, we're going to choose the minimum of those, since this question wants us to do that. And then we're going to return that amount at dp amount, which is the number of coins it takes to make up the amount. But we want to do that if and only if this isn't equal to 1 billion, which means it has actually hit this minimum case here. So that's this question. Moving on to the next one, maximum product subarray. So in this question, we're given an integer array nums, and we want to find a subarray that has the largest product, and we want to return that product. So a subarray is going to be a continuous non-empty sequence of elements. So the test cases are generated so that we can fit it in a 32-bit integer. So ints work. If you're not using Python, something like C++, you can use ints. So in example 1 here, nums is going to be 2, 3, -2, and 4. So 2, 3 is the largest product. If we include this -2 here, then we're going to get a negative number, which is obviously going to be smaller. So if we don't include the -2 here, we can try on its left, there's 2 and 3. And on its right, there's 4. So 2 times 3 is going to be 6. That's greater than 4, so we're going to return 6. So in example 2 here, we have -2, 0, and -1. So the output is going to be 0, because otherwise it's going to be -2 or -1. So 0 is going to be the maximum, so we're going to return 0 in this case. So to solve this question with a DP approach, or dynamic programming, we can keep track of our current maximum product, or our current product, starting from the left and going on to the right. And whenever we encounter a value that is 0, we're going to reset cur to 1. So we can continue multiplying with the numbers in nums, because if we hit 0, then it's going to be 0 from there on, but we don't want to include 0 in our maximum product subarray. So in this question, we can start off by setting n equals to the line of nums to make our lives easier, and our current product, that's going to be 1. We set it to 1 so we can start multiplying 1 by values in nums. And our product, this is going to be the maximum product that we're going to return. This should be initially be set to nums at 0. So whatever value this is, and we're going to update it to the maximum as we get other products. So for every number in nums, so for I in range, starting from 0 all the way to len nums, so our cur, this is going to be multiplying equal to nums at I. And product is going to be the maximum of product and our current value. This updates product to whenever cur has a greater value than product, we're going to update our product to that, and we're going to return product at the end. However, if we hit a 0, so if cur equals to 0, so cur is going to equal to 0 whenever nums at I is equal to 0. So if this is the case, we're going to reset cur to be 1. Because suppose we hit a 0, suppose this number here, the 3, this is actually a 0. We still want to try numbers after it, for example, the 4. So we're going to set cur to 1, otherwise it would make everything else after that 0. Now after that, we can just return prod. However, there's another trick in this question. Because this question involves negative numbers, there's two different cases with negative numbers. So there's one case where there's an even number of negative numbers in the nums array. So if there's an even number of negative numbers, then we don't have to worry about them being negative, because when an even number of negative numbers multiply together, that's going to create a positive. However, there's a case where the number of negative numbers is going to be odd. So if there's an odd number of negative numbers, for example, in example 1 here, there's one negative number and negative 2. So we don't want to include this negative 2. So if we call this for loop starting from the front and then going all the way to the back, so from left to right, this is going to only encompass the products or the maximum product subarrays on the one side of the negative number. But we also want to consider products on the other side of the negative number. So another way to look at this is, let's suppose we have a little diagram here. Let's suppose n is going to represent negative numbers, and we have a maximum product subarray where there's 3 negative numbers. So looking at any negative number here, for example this one, on the left of it is going to be a product subarray where there's an even number of negative numbers, which is 2. So on the right of it, there's also an even number of negative numbers, which is 0. So looking at the negative number on the other side, on its right side, there's an even number of negative numbers, with being 2, and on its left side, it's also 0. So for the leftmost and the rightmost negative numbers, we're going to want to consider all the product subarrays on their lefts and their rights. So to cover all these cases, we're going to need to do this for loop not only from the left to the right, but also from the right to the left. Because, for example, this case, this would never get covered by our for loop, but it would get covered if we started from the left side and we traverse to the, if we started on the right side and traverse to the left side. So let's code that real quick. So let's reset cur to be equal to 1, and for I in range len nums -1, -1, -1. This is just a Python syntax to start at the last index and 1 before -1, so end at 0, and also step -1. So move back 1, basically. And we're going to do the same logic. So cur multiply equals to nums at I. Product is going to be the maximum of product, or if cur is greater, it's going to be cur. And again, if cur hits 0, we're going to want to reset cur, because otherwise that stops any calculation from then on. Since 0 multiplied anything by 0 is 0, so we're going to reset cur to 1. So let's try running this. Cool, it's accepted. Nice. So this question, the logic is pretty similar to Cadane's algorithm. If you guys have done maximum sum subarray, you would have seen that algorithm. But the trick here is that we have to not only look from the left to the right, but also from the right to the left, because it's possible that our maximum product subarray or our total subarray has an odd number of negative numbers, in which case on its left and its right side, there's going to be an even number because we're taking out this odd negative number here. So to encompass for all the cases, especially the ones on its right side, we're going to need to start traversing from the right side to the left side. So we're going to do 2 for loops in range n, so it's still O of n algorithm, but it's just going to be starting from left to right and then starting from right to left. So moving on to the next question, word break. So in this question, we're given a string s and a dictionary of strings word dictionary. We want to return true if s can be segmented into space-separated sequence of 1 or more dictionary words. So let's look at some examples here. So, also, words in the dictionary can be reused multiple times. So in example 1, we have LeetCode. The word dictionary is leet and code. So obviously we can combine these words to form LeetCode, so we output true. Example 2 here, we have apple, pen, apple. We can use apple, so we can use pen between 2 apples, and that's going to be true because we can reuse apple as many times as we want. So in example 3 here, there's cats and dog. So suppose we start off with cats, then we are left with A-N-D-O-G. So A-N-D-O-G cannot be broken up into any more words because if we use and dog, there's 2 Ds. So suppose we use cat at the start instead of cats, so then we can use sand. So if we use sand, we're left with OG, but OG is not in word dictionary. So in any of those cases, we cannot actually complete cats and dog, so we're going to return false. So this question is a dynamic programming question because we can look at starting from every index. So we're going to start from index 0, and we're going to try all the possible words, and then we're going to record what the next index that is valid until. So for example, in cats and dog here, we start at index 0. We see that, hey, we can use cats or we can use cat. So both the index starting for A and the index starting for S, these are going to be valid starting points. So S is because we used cat before, and A is because we used cats before, the plural. So it doesn't matter, we don't have to do anything with word dict because we can use these words as many times or as few times as we'd like. So we can just keep trying from every index on which words we can use and see if the next index is going to be valid. So in the end, how do we see if the entire string is valid? We're going to look at the index one after the word. So one after the word ends, we're going to see if this is a valid starting index. Because if it was, then a word would have set this to be true. So let's do the code. First of all, let's actually just create n equals to the length of our string s. And dp, we're going to set 0 for n plus 1 because we want to access the nth index, or the one that after the word ends. And here, dp being equal to 1, or dp I equals to 1, means we can start from the ith index. So of course we can start from the 0th index, that's like a given, so dp at 0 is going to equal to 1. So now for every index we want to look, so for I in range n here, basically we're going to look at every index before n, and we're going to see if we can use a word to populate or validate a future index. So let's look at the words. So at first, if dp I is equal to 0. So if this index is equal to 0, remember dp I equals 1 means we can start from this index. So if it equals to 0, that means we cannot start. So if we can't even start from this index, we should just continue and try the next index. So continue. So for word in word dictionary, so for example, we're at index 0 and we're given this whole word dict. So we're going to compare the substring starting from index I, or index 0, and going as long as the word to see if we can match the word. So to get the length of the word, we can just do wordlen equals to the length of the word. So if word is equal to s sliced at starting from index I, or index 0 in this case, and then as long as the word length, so I plus word length. So if this case is true, so if word is actually equal to this slice here, then we should validate the next index, or the index after this word ends should be 1, because we can actually start from that index in the future. So dp at wordlen plus 1, or plus I, this should equal to 1. Because wordlen plus I is where this slice ended, which is going to be the start of the next word. And after that, we said all we have to check is whether or not we can start from 1 after the word ends. So 1 after the word ends is going to be at index n. So we can return dp at index n. Let's try running that. Cool, it's accepted. Nice. So this question, we're basically taking a dp array, and what dp array stores is the validity of the index. In other words, whether or not we can start at a certain index. So 0 basically means false, 1 means true. So if it's 0, we can't start at a certain index. If it's 1, we could start at that index. And then we traverse all indexes from left to right, and then we see if we can populate or validate a future index. So if we validate that future index, we set it to 1. And in the end, we want to see if some of the words in the range have set the index after the word ends to be true, or to be 1. So if they did, that means we can word break, otherwise we can't. So moving on to the next question, longest increasing subsequence. So in this question, we're given an integer array nums, and we want to return the length of the longest strictly increasing subsequence. So a subsequence is an array that can be derived from another array by deleting some or no elements, without changing the order of the remaining elements. So in other words, a subsequence is like a subarray, but it doesn't have to be continuous. So let's look at the examples here. In example 1, the longest increasing subsequence is going to be 2, 3, 7, and 101. So 2, 3, 7, 101. So notice we can also do 2, 3, 7, and 18. That also works. So the length of that is going to be 4, so we want to output 4. In example 2 here, we have 0, 1, 2, 3. That's also going to give us an output of 4, or a length of 4. In example 3 here, everything is 7, which means that there's nothing that's strictly increasing except a number itself, so we're going to output 1. So this question is going to be a DP question because we can store the longest strictly increasing subsequence ending at every index. And then we can take a future number, for example 101, compare it with all the previous indices, seeing as long as 101 is greater than the number there. So if 101 is greater than the number there, we can concatenate 101 to the strictly increasing subsequence at the previous index. For example, we derived that 2, 3, and 7, that's a strictly increasing subsequence. So we can concatenate 101 to the end of that sequence. So it's going to be 2, 3, 7, and 101. So that's a strictly increasing subsequence, and the length is going to be 1 plus the length of the previous strictly increasing subsequence. So let's set n equal to the len of nums, and our answer to be 1. Because at least we can have one number. In the case of it's all 7s, at least one of them is strictly increasing. So the number itself, 7. So dp equals to at least 1 times n. So now for I in range n, so basically for all numbers from 0 all the way to n, we're going to look at all the previous numbers. So basically if I is here, the index of 101, then we're going to look at all previous numbers. So j is going to end at 7. So for j in range from 0 all the way to I. So basically for all previous numbers, first we have to see if our current number is actually greater than the previous number. If it isn't, then we can't say it's a strictly increasing subsequence, right? So if nums at I is, or is less than, if nums at j is less than nums at I, so this is what we want. If the previous number is less than our current number, then we can concatenate our current number to the strictly increasing subsequence ending at the previous number. So dp at I equals to the maximum of whatever we have at dp of I, or one number plus dp at j. So this one number is concatenating our current number, and dp at j represents the length of the longest increasing subsequence ending at j. So, and we only want to do this when I is greater than j, or the nums at I is greater than nums at j. And after every loop at I, we can try to see if our answer has increased. In other words, the longest increasing subsequence is ending at index I. So our answer should equal to the maximum of answer, or dp at I. After that, we can just return our answer. Let's try running it. Cool. Let's submit it. Nice. So in this question, we're storing the length of the strictly longest increasing subsequence ending at index I into dp. So for all future ones, we can take a look at whether or not the future number is strictly greater than the previous number. So numbers I is greater than nums of j. If it is, then we can concatenate this number at I into our strictly increasing subsequence to create a length of 1 plus dp at j, so one more than the previous length. And then at every index I, we're going to compare dp of I, which is the maximum length, with our answer to update our answer. And then in the end, we can just return our answer. So that's this question. Let's move on to the next one, which is partition equal subset sum. So in this question, we're given an integer array nums, and we want to return true if we can partition the array into two subsets such that the sum of the elements in both subsets is equal, or false otherwise. So in example 1 here, we have 1, 5, 11, 5. We can partition the numbers into 1, 5, 5, and 11. So that's going to be equal. So in example 2 here, we have the numbers 1, 2, 3, 5. So this is going to be false because we can't partition them into two equal sum subsets. So one thing to note here is that 1, 2, 3, 5, that sums up to 11. 11 is odd, so obviously we can't partition them into two equal sum subsets. So immediately we should return false if we realize the sum of nums is going to be equal to an odd number. So let's create total. Total is going to be equal to the sum of nums. So if total mod 2 equals to 1, that means we're going to have a number left over when partitioning into two equal subsets. So we're going to return false immediately. So next, we realize we want to basically create a subset of this numbers, of nums, that adds up to half of the nums. So the sum in example 1 here is going to be 22. So we want a subset of nums that sums up to half of 22, which is 11. So obviously we can just take this 11 here. And what we have remaining is going to be the other half, which is also going to sum up to 11. Since 22 is an even number, and we took away half of it, then the remaining is going to be the other half. So in this question, it boils down to actually taking a subset of nums and seeing if we can create half of the sum of nums. So our goal here is going to be half. Half is going to be total divided by 2. So after we made sure that total is an even number. So dp, what is dp going to store here? dp is going to store all of the possible valid values starting from 0 all the way to our goal, which is total. This is kind of similar to the coin change idea, but in this case, it's whether or not we can actually reach that number. So which values do we want to reach? All the values starting from 0 and all the way to half plus 1. So this is going to be an array with index 0 all the way to half, because we want to see if half is true or not. So we need to do an array of length half plus 1. So starting off dp at 0, this is obviously reachable because we can just not use any elements, and we're going to reach a value of 0. So dp0 equals to 1. 1 indicates it's reachable, and 0 indicates it's not reachable. So dpi equals to 1 if I is reachable. Reachable just means it's summable. Let's say summable by some subset of nums. Cool. So now let's look at all the numbers in nums. Since we can only use each number once, we can start off our for loop by traversing which numbers we're going to use. So for num in nums, so now we're going to look at every possible range starting from 0 all the way to half. So for I in range starting from 0 all the way to half, so half plus 1. So we want to see if dp at I is going to be equal to 0. So if dpi not equal to 0, that means I, the current index, is actually reachable. So if the current index is reachable, and we should also check that I plus num, so we're basically using num on top of our index I. So I is an amount. If amount plus our new number is less than half plus 1, so if it's actually inside the range of the array, then we're going to set our dp I plus num. This is going to equal to 1. So basically we validated the new index I plus num. This is going to be set to 1. Because we know that we can reach dp at I, and we also have a number num that we haven't used before. So that means dp I plus num should be set to 1. However, in this question, there's actually a weird case where we're actually changing values at dp, and we're going to continuously change those values. So for example, if nums at, so the number we're dealing with is 1 here, so if num equals to 1, then for every number, starting off dp0 is not going to be equal to 0, and it's going to be in the range. So we're going to set dp1 to 1, and then I is going to become 2, and then we're going to set dp2 to 1, and then dp3 to 1, dp4 to 1, so on. This is because we're using the number 1 more than once. So to avoid this case, we're going to create a new dp. So this is going to be dp.copy. And because we can only use each number once, we can reset the dp to be equal to new dp after trying each number. So after this, dp should equal to new dp. After that, we can just return dp half. If dp half is 0, that means we can't reach half. If it is equal to 1, that means we could reach it. So this is going to be the answer to our question. Let's try running that. Wrong answer. Oh right, it's because I'm using dp here instead of new dp, so I should use new dp, and let's run it. Cool, that worked. Let's submit it. Nice. So this question is mostly pretty straightforward. First, we calculate the total. After we get the total, if it's an odd number, we return false instantly because that can't be broken down into two equal sum subsets. So next, we find our goal that we're trying to reach, which is half. We create a dp array. The trick to this question is actually creating this new dp and setting dp to new dp after we're done. So the reason we have to make a new dp array is because within the loop of each number, we don't want that to affect itself. Because otherwise, we can just use a number 1 and use that number more than once. So we only want to use each number once, so we're going to compare with the previous dp and set values in new dp. And then set our previous dp into new dp. In the end, we can just return dp half. This is going to be 1 if it's summable, and it's going to be 0 if it's not summable. So that's it for this question, and that's it for the DP questions, or 1D DP questions in the LeetCode roadmap. So thank you guys so much for watching. Hope you were able to learn something, and I'll see you in a future video.